Yeah, I guess I come in a natural position in these sort of talks because we're coming at the end here, and we are fundamentally dependent upon everybody else in this room to get to the point where we start our piece of the work. So to explain a little bit about Williams. Williams is probably known to you as a Formula One team, and perhaps less known to you as the technology commercialisation business that I work for. So we are taking the products of, millions and millions of pounds of development to send 2 cars around a track. Not terribly fast this year, but two cars around the track. And we are taking that and applying it more widely within other industries. We have a particular advantage in this industry in that we, in 2009, when CARS, the Kinetic Energy Recovery System, was introduced into Formula One, we had developed our own system. And so we already had battery, inverter and motor knowledge, which we brought to this. So our sort of broad list of skills that we bring are shown here, but really the bit that I want you to focus on is this high-performance hybrid and EV part, and that's what I'll talk about. Also important is lightweighting, but it's to a lesser extent than that. So our role in this whole sort of big industry, if you like, is to try and take a cell and turn it into a pack. So the first sort of thing for us to do is to try and take a view of the commercially available cells, screen them for the best one for a given application, and then we have to transform that into a module. A module is one of the subcomponents of the pack, and it's a fundamental building block that every manufacturer uses. Once we have that module, then we have to transform multiples of that module into a pack, and fundamentally where we end up is delivering something that goes into a car like this. So, nice glossy Aston Martin picture. Quite pleased that I got the best pictures. So given that's quite easy, what is our real challenge here? Well, here is a sort of graph showing the cells that are available in the market today. Some of these are not really market cells, but they are available. They are being made in low volume. And so you can see that if you start on the left-hand side of the graph, you start with sort of things which are designed specifically for motorsport. They're super high in terms of the power capability that they have, so 18 kilowatts per kilo, but their energy density is very, very low. When you come across the right-hand side of the pack, of the graph, then what you see is that we have very high energy capability cells, but they really have very poor power capability. And so that's kind of our challenge, is if you want to have a battery which has both very high energy and very high power, how do you get there? So this is where I guess the cleverness that we have comes in. So we have opted to do things like this. So this was presented last month at the Low Carbon Vehicle Show. Let me just see if I can get all the points up on screen. So this is a hybrid module. So it uses 2 different types of cell, an energy cell and a power cell, in combination with a DC-DC converter that shuttles power between the two. So you can see in my sort of very simple little drawing on the bottom left, basically we have a group of very high power cells which are connected to the load, and fundamentally, if you consider them to be a bucket, we pour water from the energy bucket into the power bucket to deliver our load, the power for our load. That is a relatively simple concept. It's not been a concept that's been deliverable until quite recently, and up till now it's not a concept that's really deliverable for anything other than some quite specific applications. But as the higher energy cells come along, that will come to the market, then this becomes much, much more a feasible product for the future. So the second area where we work, and again I'm kind of quite blessed with some of the technology which I inherited, is in battery management, and then the algorithms that we can apply within battery management. So one of the sort of benefits of come from a Formula One background is that I inherited what looked to be like a totally crazy battery management system which had the highest power processor that I'd ever seen, and really was not the sort of commercial thing that Tony might have seen in his past life. It wasn't the cheapest chips processor delivering the minimum that was required to deliver an application. It was a very high complexity processor, and yet we were making relatively little use of it. So we had the opportunity to work closely with people like Greg Offer at Imperial and take the modelling sort of capability that he was generating through the Faraday institution, and to try and pull that through into our BMS, try and give more power and more capability. And when you do that, one of the things that you can do, because we're fundamentally limited in terms of the energy that's in a cell, but if you model it more closely and you know where the limits are that you're operating to, then you have the possibility to use more of that energy, more of that power, to do faster charging and still sort of deliver the same results as you would have previously. The other sort of area where we work is obviously on the mechanical and thermal aspects of batteries. So we're taking the available cells and we're trying to combine them in the most efficient way possible. Fundamentally we want the minimum number of ancillary materials to add to the cells to create a module and then to create a pack. And so we do this, through the use of sort of innovation in techniques and new materials, and we deliver the most efficient module that we can from an energy and power density perspective. And we end up in this. We end up with these sorts of products that we're enabling. And we will continue to do this. We really think that we are at the cutting edge of this. We are wholly dependent upon the money that government is putting in to enable this. We would not have made the contributions that we've made without it. So there we are. Thank you very much.